Okay, in this video we're talking about how do you test to see if two events are independent or not. So the first test for independence is if the probability that A and B occur, does that equal the probability of A times the probability of B? So here we have a two-way table that we can fill in based on this information. A state government study of 1,000 persons shows that 950 are employed and 925 have a high school diploma. So therefore, if 950 are employed, 50 are unemployed. If 925 have a diploma, then 75 don't. If 900 are both employed and have a high school diploma, that's 900, so we need a total of 925. This should be 25. If this is 950, that means 50, no high school diploma, and here this should be 25. Okay, now that we filled out the table, let's look over here. What's the probability that a randomly selected person is employed? So we're looking at the total here for our denominator, and employed would be 950. What's the probability of having a high school diploma? So again, out of the 1,000, if you randomly selected somebody, there would be 925 that they have a high school diploma. What's the probability of being employed and having a high school diploma? So right here, which is 0.9. What about if we check to see the probability of being employed times the probability of having a diploma? So if we multiply these two above, 950 over 1,000 times 925 over 1,000, and multiply those two together, get 0.8788. So I check to see, are these two probabilities equal to each other? And they're not. If they were equal to each other, I could say that they were independent events, but because the probabilities are different, they are not independent. On the bottom of the page, here's just some simple multiplication problems. Let's see if A and B are independent. So here's the probability of A and the probability of B. If I multiply those, do I get the probability of A intersection B? So 0.3 times 0.6, yes. So A and B are independent. In this problem, here's A and B, their probabilities, so 0.6 times 0.8, and if I multiply those two together, I get 0.48. 0.48 does not equal to that intersection, so A and B are not independent. Doing the problem over here with cats and dogs, the question, the table below shows dogs and cats at an animal shelter by gender. The question is, are species and gender independent at the shelter? And show your work. So I would pick one gender and one type of animal and find out using the multiplication principle, are they independent? So let's do males and dogs. Is that the probability of male intersection dog? So let's see. If you randomly select an animal from the shelter, there's 42 animals in the shelter, what's the probability you choose a male? 14. Again, what about the probability that you choose a dog randomly? So how many dogs are there? 24. The question is, does this equal the probability of being male, a male dog? So 8 out of the 42. So if I go ahead and multiply these, 14 divided by 42 times 24 divided by 42, I get 0.1905 approximately, or as a fraction, 4 out of 21. Over here, I get 8 divided by 42, which is the same 0.1905 approximately, or 4 out of 21. So because those probabilities are the same, we would say that yes, species and gender are independent. There's a second test for probability, for independence. And the second test looks like this. Does the probability of A change given that B has occurred? If the probability of A doesn't change, then the events are considered independent. If the probability changes, they're dependent.
Please report to Ms. Davis and have.
Okay, the second test for independence is do the probabilities change given some other event has occurred? Here's that same table that we used before, and so it says, okay, what's the probability of being employed? So again, we use our total of 1,000, and out of the 1,000, how many of those are employed? That was 950. Okay, so the probability of being employed was 950 over 1,000. But now the conditional probability, what's the probability of being employed given that you have a high school diploma? So given that you have a high school diploma is 925, and out of the 925, 900 of them were employed. As a decimal, this is 0.973. What's the probability of having a high school diploma? So out of 1,000, the diploma was 925, or 0.925. What's the probability that you have a high school diploma given that you're employed? So let's see, employed, the denominator is 950. And out of those 950, the number that are employed is 900. Sorry, the ones that have high school diploma, sorry. Okay, so that would be 0.947. And this one up here is 0.950. So let's see, compare the probabilities from parts A and B. Are they equal? So is the probability of being employed and the probability of being employed given that they have a diploma equal? Those probabilities are not equal. How about compare the probabilities from parts C and D? So the probability that you have a high school diploma and the probability you have a high school diploma given that you're employed are not equal to each other. So because these probabilities are not equal and these probabilities are not equal, that we can conclude that status of employment and level of education are not independent. Not independent.